Hi everyone, my name is Alex, and today I'm with Andrew Vorashilov, are going to improve mor1kx performance a bit. So, first, oh, sorry. So, what's mor1kx? We have an OpenRISC 1000 architecture document, and mor1kx is just another one implementation of it. It was built to provide more flexibility to engineers who want to use it. And for now, it has, I guess, 4 pipelines, 7 different purposes. Espresso, Pronto Espresso, Cappuccino, and mor1kx. mor1kx is a special case. This pipeline is designed, I think it's designed by Andrew Bacharov, and I don't know much about it. So among other 3 of them, Espresso, Pronto Espresso, and Cappuccino. Cappuccino one is most sophisticated, so let's take a look at it. So it's, I guess, a classic RISC pipeline. It has 6 stages. It's single issue. It has a delay slot and bunch of optional units such as debug unit, timers, iCache, dcache, and etc. And let me explain what do we want. You see, I'm a software engineer as well, and to be honest, I didn't have any classes on computer architecture, but I'd like to get it. So I would like to get familiar with mor1kx internals. We'd like to improve mor1kx internals, I mean performance, and of course contribute to the community. Let's talk about branch predictors. While we were diving into mor1kx, we discovered that branch predictor is a rather isolated thing, and since mor1kx Cappuccino is, I mean, it has a static one. We'll talk about it later. So branch predictors is a good point to start our performance improvement. And I have to mention that 6-stage pipeline has rather small penalty for branch misprediction. Yes, I am the guy who uses FuseSock. If you know, FuseSock allows us to use, I think, 2 simulators, Icarus Relator, and also it allows us to build something for FPGAs itself, so we could run it on boards. And the first question we had, let's get branch hit rate for mor1kx default implementation running dry stone. We used FuseSock, and the approach was, we could dump VCD file and then count mispredict events. It was not a good solution. A better one, but as well, it was very naive, was to add a print function to a place when we detect branch mispredict. We could dump trace and run the simulation. So in the end, we get some trace dump where we can calculate branches executed, and then we can get a file which contains mispredicted branches, and then we can divide and get a branch hit rate. I have to tell, running 10,000 dry stone loops on Core i3 takes about an hour. So, using Icarus simulator. We tried to use Relator, but it's of course faster, but it lacks VCD support. Of course, it doesn't have.
I'm not so. I think Verilator does allow you to dump signals. I'm pretty sure I've done that before.
Yeah. Okay. I think it's it's not supported in FuseSock. So
all right. I'd believe that.
along with other red minuses you may notice. But we want to improve FuseSock, so we'll talk about it a bit later. Violator doesn't have VCD, it doesn't have trace dump or display function. Of course, running simulations, I mean, not simulation, but code on FPGA is the best solution in terms of speed. And I think it has support of trace dumping, but we wanted to have a unified solution to track events happening in the pipeline. And the solution is a performance counter unit that is described in OR1, OpenRISC 1000 documentation. Let's take a look at it. It could track up 12 different events. You may see them. It has up to 8 counters in it, and it has conditional counting. It has programmable counting conditions, but it has its pros and cons. So first of all, implementing PCU will allow us to track down events happening in the FPGA. That's our main goal, because we want to run big tests and get real results, not rest-on ones. And it has, PCU description has some cons. Well, to be honest, it has not so clear description. If you take a look at maybe branch stall event, what is it? No one knows. So I have some assumptions. And 12 events, I think it's not enough. So, and 8 counters either. So it may be insufficient to profile a real program on running. And using PCU on simulations is still slow. And that was the point where we wanted, or when we thought how could we overcome this situation, and we wanted to estimate our performance impact of implementing branch predictors, but we couldn't afford running simulation every time. And that's the point when Andrew comes in.
So we decided to implement a C++ framework to be able to quickly estimate how certain branch predictor, its hit rate, and also be able to explore the huge design space, and as a bonus to check the RTL implementation. So the framework operates on the traces from real programs executed on simulator, and it requires branch address, branch jump offset, and the ground truth. So was it taken or not taken? The branch offset is mainly used right now for the static predictor evaluation, which is used in the Cappuccino, but we are, planning to use it later as well. So we also have a generated code, but it's not yet well tweaked, so it's based on the statistics, so it uses percentage of forward branches, backward branches, and then the percentages of this exactly same branch was having the same result as the previous execution of this exactly branch. But this approach is not yet fully tweaked. We mainly use it for the starting tests and then kind of abandon it, but I think we will revive this approach because it's kind of interesting to see if this will work to generate augmented data. And yeah, that's it for the. So to be able to flexibly test the predictors, we decided to separate the addressing modes of branch predictors and the prediction units. So examples of prediction addressing was direct addressing, where just one prediction unit exists and it is used for the prediction itself. Then the G-share, bimodal addressing, and stuff like that. And the units are static unit, which is used in the Cappuccino, then saturating counter, which is commonly known, perceptrons, and neural network, and stuff like that. And also, we are able to combine, well, currently only two predictors using the saturating counters approach suggested by Scott McFarlane. But also, we are planning to expand that approach. So, a quick overview of what a perceptron is. So the perceptron is basically a weighted sum of some inputs, and the inputs in case of branch predictors are -1 if the branch in the history wasn't taken, and 1 if the branch in the history was taken. And the output is treated similar. So if the output of the perceptron is -1, then we predict not taken, and when it's 1, when we predict it's taken. And each time the perceptron mispredicts, we are trying to train it. So in case the output, well, in case the ground truth is the same as the input for particular connection, then we are increasing weight, otherwise we decrease it. So the intuition here is that this is the correlation between the input branch in the history and the output branch. There is a problem with the perceptron, however. Then in complex cases, it can overflow. So for example, if you allocated like 5 bits for the weight and you keep increasing it, it can overflow. But this theoretically can be handled as we only care about the sign of the output. We can theoretically divide all the weights on the same number, for example, by 2. In case overflow is nearly happening. But we are yet to test this. And so there is a paper which already did this per perceptrons, and their approach was to use integer math because, well, basically there are only -1 and 1s in inputs and outputs. So in this case, the actual hardware implementation is quite simple because you only need to increment weight or decrement it, not use the product of inputs and outputs. And in this approach, the authors of the paper used bimodal addressing, similar to, well, the common known bimodal saturation counter approach. And they used the shared history, which is fed to selected perceptron after the bimodal selection happens. And since the perceptron is a very special case of neural network, it was kind of natural for us to try the fully connected neural network, the general approach. And the perceptron is basically just one neuron, and it is a linear sum or the step function at the end. So no complex activation functions are used. In the fully connected neural networks, there are several neurons. There are like input connections, there are output neurons, and there are hidden layers between them. We chose to use one hidden layer, but there could be more. But then there is vanishing gradient problems occurring, but that's a different topic. We used one hidden layer, and we used several activation functions, but still there are more, and with the fully connected neural networks, there is quite a huge design space to explore. Yeah, and in our tests, actually, the neural network was only slightly better than single perceptron. So in direct addressing, it was only slightly better. In G-share addressing, it was actually even slower sometimes. Well, not slower, but less accurate. And we didn't, as I already said, explore the design space completely because there are several activation functions, there are several optimization methods. We only use the gradient descent, and we didn't use any complicated algorithm to adjust the step size for the optimization algorithm. We just used this single number, but we did vary it, but nothing fancy like decreasing it after some iterations or anything like that.
Andrew, real quick, can you just explain what the G-share addressing is?
So G-share addressing is basically you have a table of data for predictor units, and so typically in bimodal you just use the branch address divided by, well, not divided, but the remainder of the division by the amount of, by the size of the table to address the, to select certain unit. And in G-share, you have some global history pattern, which you then, I think, you are doing exclusive OR with the branch address to get the actual bucket, to get the actual branch predictor. So you kind of, this is just the algorithm of selecting one of the tens or thousands even units that you have trained on some current program that's running. So there is also a paper that does implement the fully connected neural network. Their implementation uses fixed point math instead of floating point math just to decrease the complexity. And even despite that, the hardware implementation is quite complex even for a, well, for a single layer neural network. Also, they are using the lookup table to approximate the activation function because, well, calculating hyperbolic tangents inside of the hardware is not the best way of doing this. And here are some results that we got with our predictors in the core mark. So the x-axis is the size of the predictor in bits, and y-axis is prediction accuracy. And I hope you can see that for really small sizes of the branch predictor, this G-share with saturating counter unit, which is most widely used, I would say, in junction with others in combined branch predictors, it is winning. But then first bimodal addressing with perceptrons starts to win, and on really big predictors, the G-share addressing with perceptrons starts to win, and you can get 97 or even 98% of correct prediction rate on the core mark. Here are results for the dry stone, but dry stone was quite a simple task for the branch predictors, so you can see that they all perform quite well. Perceptron-based predictors are still better than saturated counters, G-share, but they all flat out around 95% or so, so maybe it's not that important there. So at the moment, I already explained the situation with the sizes. At the moment, using the fully connected neural network doesn't seem justified because they are far more complex in terms of hardware implementation, but the win that you get is not even nearly enough to justify the cost. And also, well, that's common knowledge, general knowledge, but combining two branch predictors using the Scott-McFarlane technique usually tends to show better from the two worlds. So the result is the best of two, kind of. So in the future work, we would like to also explore additional design space that is hashing, proper hashing. So for example, there is traditional bimodal branch predictors. One green here is addressed using the, well, like branch address and reminder of the number of the table entries. Another one is hashed, branch address hashed by the Knuth hash function. And to the right, you can see the Jenkins mix function, which given that the whole of the other part of the prediction unit is similar, it just gives you flat 0.3% increase. So this is maybe something that worth checking out. But I want to note that Jenkins mix hash is too complex to be implemented in the hardware. Well, it's not too complex, but it will be too heavy because it contains several sequential additions, shifts, and somewhere multiplications, which can be also represented as several sums and shifts. But it's not justified, again, for this win. But we kind of work to explore this field better and probably find a hash function that will be both lightweight to implement in hardware and give some additional benefits for the predictor. And yeah, so additional items for the future work is to fix the generator and try to gather statistics on some known traces and see if the predictor results will match, and based on that, see if it can be used to further understand what makes each predictor better in terms of the code. Maybe it will allow us to select certain type of predictors for the combining units better, or anything like that. Also, well, yeah, of course, there is the need to explore the design space better because it's really huge, it's multidimensional, and it needs to be done. Also, probably it would be a good idea to at least estimate the neural networks or perceptron, well, basically machine learning approaches to some other parts of the pipeline, like cache eviction policies or anything like that. And another one is to try networks with different topologies, like recurrent neural networks or long short-term memory networks or anything like that. And probably even try deep, well, not deep, but reinforced learning to try to improve prediction rates. And yeah, I think Alexei will continue.
So, as I mentioned before, we have some problems with FuseSock. We need, or we have to implement support for trace dump. As far as I know, it has been done maybe in ORCONF v2. So we just need to port it to the FuseSock. We need to implement std-out support for relator. And that has been done by Daniel. Yeah, thanks. We just need to merge it into the sources and ship it. And I think it's a good idea to extend OpenRISC specification in terms of system registers and introduce a system register that will contain a tick numbers happened after the system starts. So anyone using OpenRISC could just read from that register, and he could know how many ticks has passed since that time, and that's the way he could he could get time passed. That slide contains references Andrew mentioned. And let's sum up what do we really contribute. So we've done performance counter unit, and it's almost in the mainline sources. We've implemented rating counter that it's not quite good. It's even worse than static one, but anyway, we've done G-share predictor that it's quite good, as you noticed, and we contribute the software framework Andrew was talking about. I guess that's it. Thanks.
That was good. That was far more complicated than I was expecting to see. So I have a question. What sort of reduction in cycle count did you get when, say, you had your branch predictor 80% accurate? Just on core mark, say, like how much faster was it?
Daniel knows the answer, but as you recall, I've mentioned that performance gain will not be
Like
significant.
Okay.
For dry stone, it's about 2%. I mean, that's something, but before, using static branch predictor, we get n cycles, and using G-share predictor, we got 0.98 of that cycles.
2%. Do you know how much more area as a percent of something like the Cappuccino pipeline you got when you implemented the more sophisticated, say, G-share approach?
Well, G-share is quite, I think we could estimate their area consumption. Basically, it's 2 bits multiply history number. Sorry, sorry. Memory consumption is 2 power history bits number. So that's the result of 93% hit rate for dry stone. I think we got with size of history about 12 or 11 maybe.
Okay, so you're saying the predominant area in this is the memory that you need. So it's like the number of flip-flops that you're going to store your results in your memory bits.
Yeah.
Which I guess makes sense. Cool. All right. Did you want to say anything about Dan, did you want to say anything about the performance increase? Curious to know.
Well, actually, I'll be talking about a little bit about open risk performance tomorrow, so I'm going to avoid the performance discussion today. I did have one comment for the open risk maintainers. I do have the integration into Verilog of a standard in, standard out based on either a TCP/IP port or the standard console. So when you're running Verilator, you can use the console. It actually does a full decode of the UART protocol to the console. So if anyone wants to chat with me about how we managed to integrate that in, I'd be happy to chat. But the question I had, and I don't know how much this is directed at Alexei versus somebody else more familiar with OpenRisk, doesn't the OpenRisk's architecture have a special register for tick counts? I know a lot of processors do. I noticed Alexei said there wasn't a tick count measurement. Did I miss something in the CPU when I'm not as familiar with the OpenRisk CPU.
As far as I know, it doesn't have it right now, but I suggest to introduce it.
So I would recommend it, certainly.
Actually, I was interested about your selection of benchmarks. Initially, I was surprised that from all in G-share, but when I've seen CoreMark, I've understood why. Actually, CoreMark is not a good benchmark for branch prediction at all, and I'm interested, why have you selected it for such research?
To be honest, it was selected for no reason.
So
it's one of the most popular benchmarks, so we wanted to maybe not to measure accuracy of the branch predictor itself, but the impact that it gives us on the performance itself.
yeah, so I can explain what happens with your branch predictor when you operate on large memory sizes.
Yeah, we know that.
Yeah, CoreMark doesn't have so many branches inside, and G-share, thanks to its implementation, just caches all branches, and when you just iterate multiple times on CoreMark, you get almost exact branch prediction.
Yeah.
So if you want to really test Jenkins predictors and other stuff, actually there are many two-level branch predictors, and these ones are not the state of the art. I can send you references later if you want. Consider using something like EMBC at least, because you will get completely different results on these benchmarks.
Thanks.
I'll follow up on offline.
Yeah, FuseSock got VCD support for Verilator.
Okay.
And then if you package your core for FuseSock, everyone can use it.
Good news. Any other questions? Huh? What is FuseSock? Yeah. All right, that's it. Cheers, guys. That was impressive work. Thanks a lot.
Thanks.